Right now, you are moving. Faster than any rocket ever built. Our entire galaxy, with you inside it, is racing through space at 1.3 million miles per hour, dragged towards something we cannot even see. Ahead waits a hidden giant with the mass of 10,000 galaxies, a void that shoves us from behind, and a flow so strange it may break physics itself. If wonders like this pull you in, subscribe and ride along. Buckle up, we begin. Sit still for a moment. Feel how solid the ground is beneath you. Nothing moves. That feeling is a lie. Under your feet, the Earth spins. At the middle of the planet, that spin runs at about 1,000 miles an hour, faster than a passenger jet, and you never feel a thing. The spinning is the smallest part. The Earth also loops around the Sun. It covers that enormous circle at 67,000 miles an hour. By the time you finish this sentence, you have travelled a few hundred miles through empty space. Now go bigger. The Sun refuses to hold still either. It drags Earth and every planet around the centre of our galaxy. That orbit runs at close to 500,000 miles an hour. One full lap takes 230 million years. The last time the Sun sat where it sits today, the first dinosaurs had not been born. Bigger still. The whole Milky Way floats inside a small crowd of galaxies we call the local group. That crowd turns and falls together, tugged by heavyweights like the giant Andromeda galaxy nearby. And the local group is doing something stranger than all of it. The entire group is racing in one clear direction, moving as one, as if reeled in by a hand nobody can see. Picture a woman walking to the front of a moving train. The train rolls down the track. The track rests on a spinning planet. The planet circles a star. The star sweeps around a galaxy. Every motion stacks on top of the one below it. You are that woman, and you are doing every layer at the same time this very second. Add all the layers together and one number falls out. The Milky Way is moving at around 1.3 million miles an hour compared to the oldest light in the cosmos. That is the speed of the whole galaxy. Not just the Sun, not just the planets, the entire spiral, with its 200 billion stars, sliding through the dark like a coin flicked across a table. Here is the part that should stop you cold. Almost none of that speed comes from the birth of the universe or the simple stretching of space. Something is pulling us. Something with monstrous mass. Something parked in one fixed direction in the sky, hauling us closer every second. For most of human history, nobody had a clue. People looked up and saw stars that seemed frozen in place. The idea that our whole galaxy was falling toward a target would have sounded like madness. And here is the strangest part. You feel none of it. No wind rushes past your face, no floor tilts beneath your feet. Space gives you nothing to push against, so the fastest journey imaginable feels exactly like sitting still in a quiet room. That perfect silence is a large reason the truth stayed hidden for so long. Then, in the 1970s, astronomers stumbled onto the proof by accident. They aimed their instruments at the faint glow left over from the birth of everything, expecting it to look identical in every direction. It refused to. The map came back lopsided, skewed, warped in a way that whispered of motion on a scale nobody was ready for. That crooked glow was the first fingerprint of the force pulling us. To read it, we first have to understand the strangest photograph ever taken. The photograph is a picture of the universe as a newborn. When everything began, the cosmos was a searing fog of light and heat. As it grew, it cooled. That first light never vanished. It spread out and faded until it became a faint hum of microwaves soaking every inch of space. We call it the cosmic microwave background. It is the oldest light there is. 2 engineers found it by chance in the 1960s. They kept hearing a hiss in their antenna and could not scrub it out. They cleaned the dish. They chased off nesting birds. The hiss stayed. That hiss was the afterglow of creation itself, arriving from every direction at once. Today that light sits at about 2.7 degrees above the coldest temperature possible. It is stunningly smooth. Point your detector anywhere, and you get almost the exact same reading. Consider how strange that smoothness is. Light that has travelled for well over 13 billion years, arriving from every corner of the sky, comes in at almost precisely the same temperature no matter where you aim. The early universe was ironed flat to a fraction of a degree, which is exactly why the one lopsided feature in it stood out so sharply. Almost. When astronomers built careful maps, they caught a pattern. One half of the sky glowed a touch warmer, the opposite half glowed a touch cooler. The gap was tiny, less than 1/100th of a degree buried in the noise. That small tilt carried a giant message. Light changes colour when its source moves. Race toward a wave and you squeeze it, pushing it toward the blue and warming it up. Fall away from a wave and you stretch it, pulling it toward the red and cooling it down. You hear the same trick with sound. An ambulance rises in pitch as it rushes at you and drops as it speeds away. The warm patch marked the direction we were charging into. The cool patch marked the space we were leaving behind. The whole galaxy was blue shifting the sky ahead and red shifting the sky behind. Astronomers gave this lopsided glow a name, the dipole. It is the single largest feature in the entire background sky, bolder than any other wrinkle in that ancient light. Every map of the young universe must first subtract this warm and cool tilt before the fainter patterns beneath it can be seen. Our own motion, put simply, is the loudest thing written across the oldest light there is. Run the numbers and the speed appears, 600 kilometers every second, 1.3 million miles an hour, all of it aimed at one region of sky, toward the southern constellation of Centaurus. Think about what that means. Our galaxy was falling. The oldest light in existence had handed us a compass, and the needle pointed straight at something enormous. The warm spot was a target painted on the sky. Astronomers had a direction and a speed. What they lacked was the culprit. Nothing bright enough sat in that patch of sky to explain a pull that strong. The thing yanking on us stayed invisible. To hunt it down, they needed a way to weigh the emptiness, and the tool they reached for would drag a hidden monster into the light. There was a problem, and it was a big one. The universe is expanding. Space itself stretches, and that stretching carries galaxies apart. So of course, galaxies drift away from us. That motion is expected, calm and understood. It is called the Hubble flow. Picture a loaf of raisin bread rising in the oven. As the dough puffs up, every raisin slides away from every other raisin. No raisin is special. No raisin is being dragged. The bread simply grows, and the spacing grows with it. If our galaxy were only riding that rising dough, it would drift gently, in step with everything around it. There would be no warm patch, no cool patch, no compass needle. The raisin picture hides one crucial rule. In pure expansion, every raisin only recedes, each one growing more distant as the dough swells. There is no falling together, no gathering, no favoured point. If the universe were only rising dough, that calm and lonely drift is all we would ever see. But we have all three, so astronomers did something clever. They took our total motion and subtracted the part that expansion explains. They peeled away the calm drift of the rising bread and asked what was left. What was left was the mystery. Even after removing every scrap of expansion, our galaxy still charged in one direction at 600 kilometers a second. Scientists gave that leftover motion a name. They called it peculiar velocity, using the old meaning of peculiar, which is to say motion that belongs to us alone. This split became the master key to the whole field. Separate a galaxy's total motion into two parts. The calm drift of expansion and the extra tug of gravity, and the second part turns into a probe. Follow the peculiar velocities of many galaxies at once, and you can feel for the hidden masses bending their paths, like scattering iron filings to reveal a magnet you cannot see. That leftover speed cannot come from the stretching of space. It can only come from gravity. Something out there has mass, and its pull is bending our path away from the smooth flow of the cosmos. Here is how strange that is. In the biggest picture, the universe is supposed to look roughly the same in every direction. Smooth, balanced, no favoured way to fall. A galaxy should sit in its expanding pocket and go along for the ride. Ours does not. Ours is sprinting. A speed like that needs a cause with staggering weight. Not a star, not a single galaxy. Something far heavier, sitting far away, tugging on the whole Milky Way and every galaxy near us in the same direction. The astronomers now understood the shape of the puzzle. Our home was being reeled in by a mass so large it could overrule the expansion of the universe across our entire corner of space. They had proven the pull was real. They had measured how hard it tugged. They knew which way it pointed. They still had no idea what it was. To find the culprit, A small team would spend years measuring the distances to hundreds of galaxies, one careful reading at a time. What they uncovered would earn them a fierce nickname, and it would change the map of the local universe forever. In the 1980s, 7 astronomers set out to map how galaxies move. The work was slow and unglamorous. To learn where the pull was coming from, they needed 2 things for hundreds of galaxies. They needed to know how far away each one sat, and they needed to know how fast each one was travelling. Speed was the easy part. Light told them that. Distance was brutal. Space gives you almost no honest clue about how far a galaxy really is. A small nearby galaxy and a huge distant one can look nearly the same in a telescope. The team needed a yardstick they could trust across millions of light years, so they used a trick hidden inside giant elliptical galaxies. These are smooth balls of hundreds of billions of old stars. The team found that the way stars swarm inside such a galaxy is tied to how bright the galaxy truly is. Measure the swarm and you learn the true brightness. Compare the true brightness to how dim it looks from Earth and the distance falls out. One galaxy at a time they built their map. Then the pattern showed itself, and it was chilling. The galaxies were not drifting at random. Across a huge patch of sky, hundreds of them were streaming the same way, like leaves all sliding toward the same drain. Our galaxy was part of the stream. So were our neighbours. So were galaxies far beyond them. Everything in that whole region was falling toward a single point. The team could even feel the tug growing stronger the farther out they looked, exactly as you would expect if a giant mass sat waiting at the end of the flow, pulling the whole crowd inward. Reporters loved the story. The work was brutal in another way too. Each galaxy demanded long hours under dark skies, its faint lights split into a rainbow and studied line by line. A single distance could swallow a full night at the telescope. The 7 built their map the slow way, galaxy by galaxy, season after season, chasing a target none of them could actually see. Every reading was a small act of faith that a giant truly waited, unseen. At the end of the flow they were tracing, they started calling the 7 astronomers the 7 samurai, warriors chasing an unseen giant across the sky. The name stuck. The giant itself needed a name too. It was massive, it was hidden, it ruled the motion of everything around it. They called it the Great Attractor. The word landed with a shiver. It sounded like something from a nightmare, a whirlpool at the bottom of the cosmos, quietly swallowing galaxies whole. And the 7 had shown it was real, sitting out there in the dark, bending the paths of hundreds of galaxies at once. Yet naming a monster is easier than seeing it. The team had traced the flow, they had found the drain, they had pointed at the spot in the sky where the pull was strongest. When they turned their most powerful telescopes toward that exact spot, hungry for a first clear look at the beast, they hit a wall. The one place they most needed to see was the one place they could not. Our own galaxy was standing in the way. Let us fix that direction in your mind, because it matters for everything that follows. Look toward the constellation of Centaurus, low in the southern sky. Behind those stars, far past every star you could ever see with your eyes, lies the heart of the pull. The Great Attractor sits somewhere between 150 and 250 million light years away. That distance is almost impossible to feel, so let us shrink it. If the entire Milky Way were the size of a dinner plate, the Great Attractor would still be many plates away across the room. It sits far outside our galaxy, far outside our little local group, out in the wider ocean of galaxies, and it is heavy, terrifyingly heavy. The best estimates put its mass at around 10,000 trillion times the mass of our Sun. Written another way, that is the weight of tens of thousands of full galaxies, all concentrated into one region, all pulling together. Try to picture that. Take our Milky Way, with its 200 billion stars. Now imagine tens of thousands of galaxies like it, crammed into a single zone of the sky, their combined gravity braided into one gigantic pull. That is the scale of the thing dragging us, and the pull reaches absurdly far. The Great Attractor does more than tug its close neighbours. Its gravity bends the motion of galaxies across hundreds of millions of light years in every direction, our own among them. Gravity fades quickly with distance, so to yank on us this hard from that far away, the mass at the centre must be almost beyond belief. The great range only makes the required weight more staggering. This is why the expansion of the universe cannot win here. Across our whole neighbourhood, the Great Attractor's gravity is loud enough to shout over the quiet stretching of space. It grabs galaxies for hundreds of millions of light years in every direction and drags them inward, our own galaxy among them. The Seven Samurai had not found a single object. They had found a gravitational nest, a place where matter piles up so densely that the cosmos itself starts to lean toward it. Everything in a vast sphere around us is sliding that way. Whole clusters of galaxies, whole superclusters, all of it tilting toward the same point in Centaurus, like water tilting toward the low corner of a flooded floor. We are one drop in that flood, a single drop sliding along with countless others toward the same unseen low point in the dark. Here is the thought that keeps astronomers up at night. If a mass that huge sits that close, it should be one of the brightest, most crowded patches of sky we can find. Thousands of galaxies glowing together should blaze like a bonfire on our maps. They do not. When astronomers look at the exact spot where the pull is strongest, they see almost nothing. A dim, blocked, muddy patch of sky. The most important region in our cosmic neighbourhood, and it is hidden behind a curtain. The curtain has a name. The zone of avoidance. And to understand why the Great Attractor stayed a ghost for so long, we have to understand why our own galaxy became a wall we cannot see past. Go outside on a dark night, far from city lights, and look up at the Milky Way. You will see a pale, glowing band stretching across the sky, like spilled milk on black cloth. That band is beautiful. It is also a blindfold. You are looking edge-on into the flat disk of our own galaxy. All those glowing stars, all that gas, all that dust are packed into that band. It is the crowded downtown of the Milky Way, and we live out in the quiet suburbs staring back toward the city centre. The disk holds more than stars. It is thick with cold gas and clouds of dust, layer upon layer, all lined up along our line of sight. Anything distant that sits behind that band has to push its light through the entire width of our galaxy first. Most of that light never makes it. It gets soaked up along the way, and the galaxy that sent it simply never appears in our pictures. Now think about what that means for anyone trying to see past it. When astronomers want to study distant galaxies, they need a clear line of sight out of our galaxy and into deep space. Look up or down, away from that glowing band, and the view is clean. You can peer across billions of light years, look straight into the band, and you slam into a wall of our own stars and dust. Distant galaxies behind it get smeared, dimmed, and buried under the glare of the foreground. Astronomers gave this blocked strip a fitting name, the zone of avoidance. For a long time, people simply avoided it, because there was so little they could see there. Here is the cruel twist. The Great Attractor sits almost exactly behind the thickest part of that band. Of all the directions the pull could have come from, it came from the one direction our own galaxy hides. The most powerful gravitational feature in our region of the universe parked itself right behind our cosmic downtown, in the seat we cannot see over. Imagine standing in a stadium, trying to watch the most important play of the game. Now imagine the tallest person in the building sits directly in front of you, and never moves. That is our situation. The Milky Way is the tall stranger, and the Great Attractor is the play we're dying to see. This one accident of geometry shaped decades of confusion. Astronomers knew something huge was out there. They could feel its pull in the motion of hundreds of galaxies. They just could not point a normal telescope at it and take a clean picture. The zone of avoidance is not small either. It blots out roughly a fifth of the entire sky. A full 20% of everything beyond our galaxy is smeared behind that glowing band. Whole clusters, whole superclusters, could be lurking back there, unseen and uncounted. For years, that was the frustrating truth. The thing pulling us hardest lived in the one place we were built to be blind to. So astronomers did what curious minds always do when a door is locked. They stopped trying to look through the keyhole and started looking through the walls. They found kinds of light that slipped straight through dust as if it were glass. And when they finally turned those new eyes toward the zone of avoidance, the curtain began to lift. To beat the curtain, you first have to understand why it wins. The block in the zone of avoidance comes from two things: stars and dust. The stars flood the view with their own glare. The dust does something sneakier. It eats light. Space between the stars is not truly empty. It holds vast clouds of tiny grains, each one smaller than a speck of smoke. Spread thin across thousands of light years, those grains add up. When light from a distant galaxy tries to pass through, the grains soak it up and scatter it away. The colour of light you use decides who wins. The grains themselves are strange things. Each one is a speck of carbon or rock, often coated in ice, forged in the depths of ancient stars and flung out into space. On its own, a single grain is almost nothing. Spread grains across thousands of light years, though, and their tiny shadows stack into a wall. A galaxy behind that wall is stolen from us one grain at a time, until none of its light reaches your eye. Ordinary visible light, the kind your eyes use and the kind most old telescopes used, is exactly the kind of light dust loves to swallow. Aim a normal telescope into that glowing band, and the faint light of far-off galaxies gets absorbed long before it reaches you. The galaxies are still there, their light just never arrives. That is why the Great Attractor stayed a ghost. It was speaking to us in a language the dust deleted. Picture trying to see a friend across a smoky room. Thick smoke hangs in the air. In normal light, you see only grey haze and your friend disappears into it. The smoke does not remove your friend. It removes the light bouncing off them. Now here is the escape. Not all light is equal. Some kinds of light barely notice dust at all. They march straight through the smoke as if it were clear glass. Longer waves of light win this fight. The stubby waves of visible light get tangled in the grains, but longer waves slip between them and keep going. And the longer you go, the more the dust gives up and lets the light pass. This gave astronomers their break. If they could stop using ordinary light and start using these longer, tougher waves, they could see straight into the zone of avoidance. The wall would turn to glass. 3 kinds of vision opened the door. There was infrared, the light of heat, whose longer waves push through dust far better than the light your eyes can catch. There was the X-ray, a high-energy light that reveals the searing hot gas trapped inside giant galaxy clusters. And there was the radio wave, the longest and most patient of all, able to sail through the thickest dust in our galaxy without slowing down. Each one was a new kind of eye. Each one saw a piece of the hidden sky the others missed. And when astronomers finally aimed these eyes at the darkest heart of the zone of avoidance, at the exact spot where the pull was strongest, the blank patch was blank no longer. Shapes began to appear in the smoke. Faint at first, then unmistakable. Galaxies. Crowds of them. A hidden city coming into focus right where the monster was supposed to live. The first hidden shapes to sharpen were the great clusters, and X-ray light gave them away. A galaxy cluster is a huge swarm of galaxies bound together by gravity. Between the galaxies floats an ocean of gas, and that gas is savagely hot, heated to millions of degrees by the crushing pull of the cluster. Gas that hot glows in X-rays. Here is the gift. That X-ray glow shines straight through the dust of the zone of avoidance. So even where visible galaxies vanish behind the curtain, their hot gas still lights up like a beacon in X-ray eyes. Find the glow, and you have found a giant cluster hiding in the blocked band. Infrared eyes did their own work. Every galaxy is packed with cool stars and warm dust that pour out heat, and heat is infrared light. Special surveys swept the sky in infrared and caught the faint warm glow of galaxies buried behind our own. Thousands of them surfaced, galaxies no one had ever catalogued floating in the smoke. Then came the radio telescopes, and they had a special power. Radio waves are the giants of the light family. They're waves far longer than anything your eye can register. A wave that long barely notices a speck of dust. It slides past the grains as though they were not there, crossing the thickest part of our galaxy without losing its way. For a signal trying to escape the zone of avoidance, that patience makes all the difference. Hydrogen is the most common stuff in the universe, and galaxies are full of it. Cold hydrogen gas gives off a faint radio signal at one exact wavelength. That signal is like a fingerprint. Wherever you catch it, you know a galaxy full of gas is sitting there, and you can measure how fast it moves. Best of all, that radio fingerprint sails through the dust of our galaxy untouched. The thickest part of the zone of avoidance, the part that defeats every other kind of telescope, is wide open to radio eyes. Put the three together and astronomers built a kind of superpower, where one eye failed, another saw. X-rays revealed the hot hearts of clusters. Infrared caught the warm bodies of individual galaxies. Radio traced the cold gas that everything else missed. Slowly, patiently, they began to fill in the blank patch on the map. Not with guesses, with real galaxies, measured and pinned to real spots in space. Picture a detective in a pitch-black room, unable to use a normal flashlight. So she switches to heat vision and sees warm bodies glowing in the dark. Then she switches to sound and hears movement in the corners. Then she feels the currents of air across the floor. She never turns on a single light, and yet the whole room takes shape around her. That is what astronomers did to the zone of avoidance. They read the room without ever lighting it, and as the map filled in, the target region behind Centaurus stopped looking empty. Galaxies clumped there. Then clusters of galaxies clumped there. The blank spot was turning into a crowd. At the very centre of it all, right where the pull was strongest, one dense knot of galaxies began to stand out from the rest. A cluster so large it could anchor the whole flow. The astronomers had spent decades chasing a ghost. Now, for the first time, they were staring at its beating heart. The knot at the centre had a name once they pinned it down, the Norma cluster. It sits deep inside the zone of avoidance, buried behind the thickest dust in our galaxy, almost exactly where the Seven Samurai had said the pull should peak. For a long time it was one of the least studied giant clusters in the sky, only because our own galaxy kept it hidden. Once the new eyes found it, its scale became clear. Norma is enormous. It holds hundreds of galaxies swarming together, bound by a shared gravity, marinating in that ocean of million-degree gas. It is one of the most massive clusters anywhere near us, and it sits right at the core of the Great Attractor region, like a stone at the bottom of a drain. Finding Norma felt like victory. Here, at last, was something solid at the heart of the monster. A real cluster, weighed and mapped, sitting in the exact spot where the whole neighbourhood was falling. For a moment, the case seemed closed. The Great Attractor had a face, and its name was Norma. Then the astronomers did the math, and the victory curdled. They added up everything they could see in the Great Attractor region. The Norma cluster, the other galaxy groups scattered around it, all the mass they had uncovered by peering through the dust with X-ray, infrared and radio eyes. They totaled it all. Then they asked a simple question. Is this enough? Is all this mass piled up in the Great Attractor region heavy enough to yank the whole Milky Way and hundreds of neighbour galaxies at 600 kilometres a second? The answer came back cold. No, it was not close. The mass they had found in the Great Attractor could explain only part of our motion, something like half at best. The Norma cluster was huge, but it was too small to be the whole story. The drain was real, but the water was falling too fast for a drain that size. This was the moment the tidy story cracked open. Until then, everything had lined up. A pull, a direction, a cluster waiting at the end of it. Now the numbers refused to close. A large, real, heavy cluster sat exactly where it should, and it still fell short of explaining our speed by a wide margin. Whatever the shortfall was, it had to be either enormous and hidden, or enormous and far away. Think of it like tracking a giant footprint in the mud. You follow it for miles, sure it will lead to the beast that made it. At last you find the creature standing there, and it is only half as big as the footprint you have been chasing. Something did not add up. The pull was stronger than the visible cause. That meant one of two things. Either a vast amount of matter was still hiding, even from the new eyes, or the Great Attractor was itself being pulled by something even larger, sitting even farther away, out beyond the edge of what anyone had mapped. The Seven Samurai had found their monster, only to learn it was not the biggest one in the story. Their giant was on a leash. And to find who was holding it, astronomers had to look much, much deeper into the dark. The clue was in the direction. When astronomers looked past the Great Attractor, farther along the same line where our galaxy was falling, they noticed the flow did not stop at Norma. Galaxies beyond the Great Attractor were streaming the same way we were. The Great Attractor itself seemed to be sliding forward, drawn onward by something deeper still. Our monster had a master. The clue had been sitting in the data all along, waiting for someone to look past the Great Attractor instead of stopping at it. Galaxies on the far side of Norma were not sliding backward toward us, as they would if the Great Attractor were the true bottom of everything. They kept drifting forward, the same way we go, drawn onward by something deeper. The drain had a drain of its own. To find it, they followed the flow outward, far past the 150 million light-years to the Great Attractor, and kept going. 200 million light-years, 400 million, farther than the Seven Samurai had ever mapped, and out there, more than 600 million light-years away, they found it. A structure so large it made the Great Attractor look like a foothill in front of a mountain range. A pile of galaxy clusters packed together more tightly than almost anywhere else in the nearby universe. A true titan. Its name is the Shapley Supercluster. Hold on to the scale here because it is hard to swallow. The Great Attractor region, the thing that took decades to find, is only a way station. It is a rest stop on a much longer road, and the road runs toward Shapley. The Great Attractor is not even sitting still. It is falling too, tugged toward Shapley, just as we are tugged toward it. We fall toward the Great Attractor. The Great Attractor falls toward Shapley. It is a chain of gravity, each link heavier than the last. Picture a line of people on slippery ice, each one grabbing the belt of the person ahead. You're sliding forward because you are holding the person in front of you. But that person is sliding too, holding someone bigger, and at the front of the line stands a giant dragging the entire chain toward the low ground. Shapley is the giant at the front. This reframed everything. For years, people spoke of the Great Attractor as the destination, the bottom of the local drain. In truth, it was a stopping point on the way to a far greater pull. Now, the earlier mystery started to make sense. Remember how the Great Attractor was too weak to explain our full speed? Shapley is the missing weight. A large share of our headlong rush is not aimed at the Great Attractor at all. It reaches straight past it, toward the far heavier Shapley Supercluster beyond. We were being pulled by something twice as far away as the monster we had been chasing, and Shapley is no ordinary crowd of galaxies. It is one of the most massive concentrations of matter in the entire nearby universe, a place where clusters clump into clusters. To grasp what we are really falling toward, we have to walk up to the biggest structure in our corner of creation and stare it in the face. Shapley is a supercluster, and that word needs unpacking because the ladder of size in the universe is dizzying. Start small. Stars gather into galaxies. Our Milky Way is one galaxy, holding a couple 100 billion stars. Climb up. Galaxies gather into groups and clusters. Our galaxy belongs to a small group. Bigger crowds, like the Norma cluster, hold hundreds of galaxies at once. Climb higher. Clusters themselves gather into superclusters, vast webs where cluster links to cluster across hundreds of millions of light-years. A supercluster is a crowd of crowds, a city built entirely out of other cities. Each rung of that ladder dwarfs the one below and empties out as it climbs. Between the stars in a galaxy lies mostly vacuum. Between the galaxies in a cluster lies far greater vacuum. By the time you reach a supercluster, you're describing something almost entirely empty, stitched together by the faint, patient thread of gravity reaching across enormous gulfs. Shapley is where that thread pulls tightest of all. Shapley is one of the grandest superclusters we know. It packs together many rich galaxy clusters into one colossal knot, holding the mass of more than 10,000 galaxies like our own. It is the single most massive structure within about 1 billion light-years of us. When astronomers look for the largest gravitational feature shaping our whole region, they keep landing on Shapley. This is the true weight at the front of the chain. This is a large part of what has been reeling us in all along, felt first as a warm patch on the oldest light in the sky, back before anyone knew its name. Sit with the size of it. Our galaxy already dwarfs anything a human can picture. Now imagine 10,000 galaxies drawn together into a single dense metropolis of stars, all of them pulling in the same direction. That is the giant at the head of our flow. Even now, the Shapley supercluster is bending the motion of galaxies across an immense volume of space, our own tiny galaxy included. We have been falling toward it for billions of years, and we still are right now as you read these words. Here is the strange comfort in that. The thing pulling us is finally out in the open. Shapley shines. It sits mostly clear of the zone of avoidance, bright enough to map, heavy enough to explain most of our peculiar rush through space. After decades of chasing a ghost behind a curtain, astronomers could point at a real glowing giant and say, that is a large part of what moves us. For a while, that felt like the end of the tale, a satisfying answer. We fall toward the Great Attractor, and the Great Attractor falls toward Shapley, and Shapley is the king of the local cosmos. Then someone stepped back and mapped the whole flow at once, every galaxy, every stream, the entire pattern of motion around us. They wanted to draw the borders of our home in the universe, to trace exactly where all these currents belong. What they found was not just a bigger giant. It was a discovery that gave our entire galaxy a new address, and revealed that everything we had mapped so far was only one district of something breathtakingly larger. In 2014, a team decided to stop chasing single monsters and map the whole flow at once. Instead of asking where one giant sat, they asked a bigger question. If you tracked every galaxy in our region and followed the direction each one was drifting, where would all those streams lead? Where did the currents converge? They gathered the motions of thousands of galaxies. Then they drew the flow lines, like tracing the path of every drop of water on a landscape. And a shape emerged from the chaos. A single, connected region, where all the local currents ran inward toward one basin. They gave that region a name, Laniakea. It comes from Hawaiian words meaning immense heaven. Laniakea is our home supercluster, and its size is staggering. It stretches 500 million light-years across. It contains roughly 100,000 galaxies. Its total weight reaches about 100,000 times the mass of the Milky Way. Everything we had chased so far, the Great Attractor, the Norma Cluster, all the local galaxy groups, all of it sits inside this one vast structure. Think of what that discovery meant. For all of history, we knew we lived in the Milky Way. Then we learned the Milky Way lived in a small group. Now we learned that group lives inside Laniakea, a supercluster so large that light itself needs 500 million years to cross it. It is like a family learning, one generation at a time, the true size of their world. First you know your house, then your town, then your country. Then, at last, you see the whole continent your country was only a corner of. Laniakea is our continent. And the Great Attractor finally found its proper role. It is not the ruler of the cosmos, it is the low point of Laniakea, the bottom of the valley where our whole supercluster drains inward. All those galaxies streaming towards Centaurus are simply rolling downhill toward the floor of the place we live. There is one humbling detail buried in the map, though. Laniakea is defined by its flow, by the great basin where local galaxies gather. Our galaxy takes part in that flow. But when the team drew the borders and marked the centre, our Milky Way did not sit anywhere near the heart of it. We sit far out, away from the rich centre, away from the crowded clusters, out where the supercluster thins into faint threads. We are country cousins, clinging to the ragged edge of our own immense home, and an edge is a dangerous place to stand. A supercluster has a boundary, a line where its inward pull gives way to a neighbour's. On one side of that line, galaxies fall toward Laniakea. On the other side, they fall away, into a different supercluster entirely. Our galaxy sits close to that dividing line, which raises an unsettling thought. If we live on the border of our own supercluster, then a neighbouring giant is pulling at us from just across the fence. Our loyalty to Laniakea is not guaranteed. We're a borderland galaxy, caught in a tug-of-war between our home and the structures beyond it. To understand how astronomers drew that border in the first place, we have to picture the entire universe as something surprisingly familiar. A landscape of hills, valleys, and flowing water. The idea that mapped our home came from rivers. Stand on a mountain ridge during a rainstorm. A drop that lands on one side of the ridge rolls down and joins a river flowing east. A drop that lands a few inches away, on the other side of the ridge, rolls down into a river flowing west. That ridge is a divide. It sorts the rain into different worlds. Geographers call the whole region that drains into one river system a watershed. Every drop inside it ends up in the same place. The edges of a watershed are the high ridges where the water splits and chooses a side. The team behind Laniakea borrowed that exact picture and aimed it at the sky. In their map, galaxies are the raindrops, gravity is the slope. Instead of rolling downhill, galaxies drift toward wherever the mass piles up. Follow the drift of each galaxy, and you can see which basin it falls into. Laniakea is our watershed. Every galaxy inside it, ours included, is sliding toward the same deep basin, the Great Attractor region at its floor. Draw a line around every galaxy that drains our way, and you have drawn the border of our supercluster. Beyond that border, the raindrops choose a different river, cross the divide, and galaxies stop falling toward us and start falling toward a neighbouring supercluster, with its own basin, its own floor, its own distant giant. This was a brand new way to define our place in the cosmos. It also handed galaxies a kind of destiny. Once you know which basin a galaxy drains into, you know where it is bound over the eons to come, the way you can read a raindrop's future the moment it lands on one side of a ridge. Every galaxy in Laniakea shares our destination, sliding toward the same distant floor. We're all raindrops that landed on the same great slope. For decades, superclusters were fuzzy things with no clear edges, just crowds of galaxies that seemed loosely linked. The watershed idea gave them true borders for the first time, drawn by motion instead of by guesswork. Picture the local universe as a vast, dark landscape of valleys and ridges. The valleys are where matter gathers and galaxies pool. The ridges are the empty highlands where the pool splits. And across this whole terrain, 100,000 galaxies are quietly rolling downhill, each one following the slope of gravity toward the bottom of its own valley. Our galaxy is one of those rolling drops. We are sliding down the long slope of Laniakea toward its hidden basin at over 1 million miles an hour. There is something almost peaceful in that image, a landscape, gentle slopes, water finding its level. It makes the whole terrifying rush feel orderly, even calm. That calm is about to break. Because the watershed picture, for all its beauty, was hiding half the truth. It described the hills that pull galaxies down. It said nothing about the strange highlands that seem to shove galaxies away. When a different team looked closely at our flow, they found something the valleys alone could not explain. Our galaxy was moving too fast, and in a way that pure downhill falling could not account for. It was as if, along with the valley pulling us forward, an invisible hand was pressing against our back. Something behind us was pushing. For a long time, everyone assumed our motion had one cause. A pull. It made sense. Gravity attracts. Mass draws things toward it. So if our galaxy is racing across space, there must be a great pile of mass ahead of us, reeling us in. Find the mass, explain the motion. That was the whole game, from the warm patch in the sky to the Great Attractor to Shapley. Then, in 2017, a team led by an astronomer named Yehuda Hoffman built the most detailed map yet of how galaxies flow around us. They traced the currents in 3 dimensions, following not just where galaxies were, but where they were headed and how fast. And they noticed something the old maps had missed. Look ahead of us, towards Shapley and the Great Attractor, and you see mass, clusters, superclusters, plenty of gravity to pull us forward. That part fit. For years, this was the whole way of thinking. Motion meant mass. If something moved, something heavy had to be pulling it, and the hunt was always a hunt for hidden weight, for the giant at the end of the arrow. That habit of mind was about to slam into its limit. Now look behind us, in the exact opposite direction, back along the path we are fleeing. There, they found nothing. A yawning, empty region of space stretched across an enormous volume, holding far fewer galaxies than it should. A hole in the cosmos, and our galaxy was rushing directly away from it. That was the shock. Our motion was not shaped by the crowded region ahead alone. It was shaped just as much by the empty region behind. We were falling toward the fullness in front of us and fleeing the emptiness at our back, both at once. The team gave the empty region a name that captured the strangeness, the dipole repeller. A repeller because instead of drawing galaxies in, it seemed to drive them away. Here is why that word matters so much. For the whole history of this hunt, astronomers had been searching for hidden mass to explain our speed. They kept coming up a little short. The Great Attractor was too light. Even adding distant giants, the sums felt strained. There always seemed to be a missing push. The dipole repeller was the missing piece. Roughly half of our great rush through space is not a pull toward anything at all. It is a flight from a vast region of near nothing. Imagine a marble resting on a soft mattress. Drop a bowling ball on one side, and the marble rolls toward it, sinking into the dent. That is a pull. Now instead, lift a weight off the other side of the mattress so that side rises. The marble rolls away from the rising side just as surely. That is a push, made of absence. Our galaxy is that marble, caught between a weight ahead and a lifted emptiness behind. Both send us rolling the same way. This changes the whole feel of our journey. We are not simply being swallowed by a giant. We are being squeezed between something and nothing, driven forward by the fullness of one horizon and the emptiness of the other. But a truly empty region cannot reach out and shove anything. Emptiness has no hands. So how can a void, a place defined by having almost nothing in it, push an entire galaxy across the universe? The answer bends the way you think about gravity itself. A void does not push. Not really. To see what is happening, you have to stop thinking of gravity as a single tug and start thinking of it as a contest. Every scrap of matter in the universe is pulling on you at once. The clusters ahead pull you forward. Any mass behind pulls you back. Mass to your left pulls you left. Mass to your right pulls you right. At every moment, you're being tugged in every direction by everything there is. What you actually feel is the winner of that contest. Add up all the pulls, let them fight, and whatever is left over is the direction you move. Now imagine two sides of the sky. On one side sits a heavy region, packed with galaxies and clusters, pulling hard. On the other side sits a void, nearly empty, pulling only feebly because it has so little mass. The heavy side wins the contest. You move toward it, and from where you stand, it feels exactly as if the empty side were pushing you away, even though nothing over there is doing anything at all. The emptiness wins by failing to pull. Picture a seesaw. Put a heavy sandbag on one end. The seesaw tips toward it, and a ball set on the plank rolls that way. Now imagine the other end simply has nothing on it. With no weight to balance it, the tilt is steeper, and the ball rolls faster still. The empty end never pushed. Its emptiness just let the heavy end win harder. That is the dipole repeller. It is the empty end of a cosmic seesaw. This flips an old habit of thought. Gravity feels like a rope that always drags us towards something solid. The seesaw shows it is better pictured as a balance, weighing every direction against every other. Wherever the weight runs thin, the balance tips away, and to a traveller caught in the tilt, thin emptiness feels exactly like a shove in the back. The clusters ahead of us pull. The void behind us fails to pull, and the total effect tips us forward with twice the force, as if we were both hauled and shoved. This is why the void matters as much as the giant. Astronomers found that the pull of Shapley and the push of the dipole repeller are roughly equal partners. Take one away, and our motion no longer adds up. Together, they finally explain the full speed of our headlong rush, the speed that first showed up as a warm smudge on the oldest light in the sky. For decades, the sums had come out short. The missing weight was never a hidden lump of mass. It was a hidden absence of mass, a great nothing sitting behind us, tipping the scale. Sit with how strange that is. Part of the reason our galaxy is one of the fastest moving objects you can imagine is that a region of the universe is unusually empty. We are being expelled, in part, by a silent and enormous wasteland. And the emptiness behind us is not the only void in this story. There is another one, far closer to home. It sits right on our doorstep and we are climbing out of it this very moment. Not all empty regions are far away. One of them is practically next door. Our galaxy sits at the edge of a large, quiet emptiness that astronomers call the local void. It begins near the border of our own local group and stretches outward across a huge stretch of nearby space. Inside it, galaxies are shockingly scarce. It is one of the emptiest regions we have found anywhere close to home. And here is the unsettling part. We are not resting beside it. We are being driven out of it. When astronomers measured the motion of our local group in fine detail, they found that a good chunk of our speed comes from this nearby void expelling us. The same seesaw effect is at work. The local void has almost no mass to hold us, so the fuller regions on the far side win the contest, and we drift away from the emptiness at a brisk clip. Measurements suggest the local void is pushing our galaxy outward at hundreds of kilometers a second, a large slice of our total motion coming from a region defined by how little it contains. Sit with that for a second. Some of your speed through the universe right now comes from the fact that a stretch of space near us is nearly barren. You're being nudged along by nothing, evicted from a cosmic ghost town. Picture a boat drifting on a lake. On one shore stands a crowded city, all lights and motion. On the other shore lies a dark, empty marsh. Slowly the boat drifts away from the empty marsh and toward the bright city, carried by a current you cannot see. Our galaxy is that boat. The local void is the marsh at our back. This nearby void is smaller than the distant dipole repeller, but it is far closer, and closeness matters in gravity. A modest emptiness near you can shove harder than a giant one far away. This is one of the quiet lessons of gravity. Nearness beats size more often than you would guess. A small mass close at hand can outmuscle a titan on the horizon, and a small void close at hand can outshove a vaster one far away. Our motion is shaped as much by our immediate surroundings as by the great giants at the edge of sight. So this humble hole in our neighbourhood earns its place in the story of our motion. Now step back and look at the full picture we have built. Ahead of us, the great attractor pulls, and Shapley pulls harder still from beyond it. Behind us, the dipolar repeller drives us forward, and the local void gives us a shove from close range. Pull and push, giant and void, near and far, all conspiring to fling our galaxy across the cosmos. It feels like a complete map at last. Every force accounted for, every push and pull in its place. It is not complete, not even close. Because our maps have a permanent blind spot, that band of dust and stars we could never fully see through. And in 2016, astronomers reached into that blind spot and pulled out something no one saw coming. A giant that had been hiding in total silence for the entire history of astronomy. It rivals Shapley itself. And it had been there all along. Remember the zone of avoidance, the band of our own galaxy that blots out a fifth of the sky. For a long time, people treated it as a nuisance, a blank strip where little of importance could hide. That assumption shattered in 2016. A team led by an astronomer named René Kran-Korteweg had spent years developing ways to peer into the blocked band. They used the same tricks that revealed the great attractor's heart, radio telescopes that read the fingerprint of hydrogen gas, and large telescopes that catch the faint light leaking through the dust. Deep inside the zone of avoidance, in the direction of a southern constellation called Vela, they found galaxies, then more galaxies, then clusters of galaxies, all clumped together in a way that could only mean one thing: a supercluster. A structure on the same scale as the greatest known assemblies of galaxies in the universe. They called it the Vela supercluster. It sits about 800 million light-years away, farther than Shapley, on the far side of that dusty curtain. And it is huge. It stretches across roughly 300 million light-years of space. To put that in human terms, it is around 3,000 times wider than our entire Milky Way galaxy. Here is what makes Vela so haunting. It had been sitting there, in that spot, for the entire history of stargazing. Every astronomer who ever lived, every telescope ever built, looked out at a sky with Vela in it, and nobody saw it. The dust of our own galaxy erased one of the largest structures in the nearby universe completely. For as long as humans have watched the stars, it took a special generation of instruments, reading light our eyes cannot use, to finally lift the veil. The discovery came together the hard way, one faint reading at a time. Radio dishes caught the whisper of hydrogen gas in galaxy after galaxy, each one a pinprick in the dark band. Large mirrors gathered the little visible light that leaked through the dust. Slowly, a scatter of lonely dots became a pattern, and the pattern became a structure far too large to be anything but a supercluster. Picture a person who lives their whole life in a valley, believing they know the shape of the world around them, every hill, every ridge mapped and named. Then one day the fog that always clung to one horizon finally clears, and they see it. A mountain range, vast and ancient, taller than anything they knew, that was standing there the entire time. That is what Vela was. A mountain range revealed by lifting fog. And this was no minor find. When astronomers estimated Vela's mass, the number came back enormous, on the same scale as the mighty Shapley supercluster itself. two titans of the local universe, one we'd known for years, one that hid in plain sight for a century. The two of them sit surprisingly close together in cosmic terms, both within about 1 billion light-years of us. And that closeness raises a serious problem, a puzzle that reaches into the deepest questions about how the universe is built. Two giants, side by side, in our own backyard may be more than the rules of the cosmos are supposed to allow. Finding Vela was thrilling. It was also, for some scientists, a little alarming, and the reason cuts to the heart of how we think the universe works. The standard picture of the cosmos rests on a simple idea. On the larger scales, the universe should look roughly the same everywhere. Smooth. Even. If you zoom out far enough, no region should be dramatically lumpier or heavier than any other. Galaxies clump into clusters and superclusters, yes, but there is supposed to be a limit to how much matter piles up in one neighbourhood. Now look at our neighbourhood. Ahead of us lies Shapley, one of the most massive structures within 1 billion light-years. Not far from it, hidden behind the dust, lies Vela, possibly just as massive. And scattered between and around them are the Great Attractor, the Norma Cluster, and all the machinery of Laniakea. That is a lot of giants crowded into one corner of the cosmos. The concern is this. If our little patch of the universe holds two Shapley-scale titans so close together, then either we live in an unusually lumpy region by pure chance, or the universe is lumpier on large scales than the standard picture allows. Both options make cosmologists uneasy. It is a bit like flipping a coin. Flip it 10 times and get a few heads and a few tails and nothing seems strange, but flip it 10 times and get 10 heads in a row and you start to wonder if the coin is fair. A pile-up of giant structures in one place is the cosmic version of 10 heads in a row. It might be luck. It might be a sign that our model of the coin is wrong, and Vela deepens the worry in another way. It reminds us that our map of the local universe still has a giant hole in it. A full fifth of the sky remains hard to see. If one Shapley-sized structure could hide there undetected for a century, what else is still crouched behind the dust uncounted? Every hidden giant changes the sums. Every unmapped supercluster adds pull we have not accounted for and reshapes the flow we are trying to explain. Our neat picture of pushes and pulls is built on a map we know is incomplete. Picture an explorer drawing a map of a new land, confident and precise, filling in mountains and rivers. Then imagine learning that 1/5 of the territory was always hidden under permanent cloud, and that the one time the cloud parted, a mountain range appeared that dwarfed everything already drawn. How much would you trust the rest of the map? That is where astronomers stand. They have found monsters ahead and voids behind. They have named our supercluster and traced our fall, and they know, with certainty, that pieces are still missing. So far, everything we have described obeys ordinary gravity. Giants pull, voids let go. It is strange and vast, but it follows the rules. The next idea does not play so nicely. It is a claim so bold that many scientists refuse to accept it. A possible motion in the universe that ordinary gravity cannot explain at all. Some call it a mistake. Others call it a signal from beyond the edge of everything we can see. They call it the dark flow. In 2008, an astronomer named Alexander Kashlinsky announced something that made the field flinch. He'd been studying the motion of galaxy clusters using a subtle trick. When the light of the ancient cosmic background passes through the hot gas of a moving cluster, the cluster leaves a faint mark on that light, a whisper of its motion. One cluster's whisper is far too soft to hear. But Kashlinsky and his colleagues gathered hundreds of clusters and listened to them all at once, letting the tiny signals add together. What they claimed to hear stunned everyone. The clusters were moving together, hundreds of them, spread across a vast stretch of the universe, all drifting in the same direction at enormous speed, close to 1,000 kilometers a second, and they were streaming toward the same region we already knew about, out past Centaurus and Hydra, in the direction of our own fall. That alone would be strange. Here is what made it terrifying. The motion did not fade with distance. Kashlinsky tracked the streaming clusters out to 2.5 billion light-years, and the flow kept going, still coherent, still pointed the same way. It showed no sign of stopping, no sign of a source anywhere inside the region he could measure. He gave it a name that has haunted cosmology ever since: the dark flow. Think about what an unfading flow would mean. Every pull we have described so far, The great attractor, Shapley, Vela, comes from mass we can point to, mass that lives inside the universe we can observe. Those pulls have a source. You can find the giant at the end of the flow. The dark flow seemed to have no source inside the visible universe at all. Whatever was pulling those clusters, it lay beyond the region we can see, past the edge of everything light has had time to reach us from. A tug from outside the observable cosmos. Kashlinsky himself put it plainly. He said this was not something they set out to find, but they could not make it go away. Picture standing on a beach, watching driftwood float past you in the surf. Now imagine that every piece of driftwood, as far as you can see up and down the coast, is drifting the same way, pulled by a current so long that its beginning and end lie far beyond the horizon. You would know, with a chill, that something enormous was happening out past the edge of sight, something you could feel but never see. That is the dark flow, a current in the cosmos with its source hidden beyond the rim of the knowable universe. If it is real, it hints at things almost too big to say out loud. It suggests that the universe we can observe is only a small patch of something far larger, and that whatever lies out there, past our horizon, is heavy enough to drag whole rivers of galaxy clusters toward it. Some scientists even wondered if it was a fingerprint of another universe, tugging on ours. You notice the words, if it is real. Because from the moment Kashlinsky announced it, a storm broke over his claim. Other scientists took the same data, ran their own tests, and came back with a very different verdict. The fight over the dark flow was about to get vicious. The trouble with the dark flow is that it sits at the very limit of what our instruments can detect. The signal Kashlinsky relied on is faint almost beyond belief. He was reading the whisper of moving clusters written onto the oldest light in the universe, and that whisper is buried under the light's own natural ripples, which are far louder. Pulling a real signal out of that mess is like trying to hear one person breathing across a stadium full of cheering fans. Kashlinsky said he could hear it. Others said he was hearing things. Within a year, another researcher reran the analysis and reported that the signal was far weaker than claimed, weak enough that it might be noise dressed up as a discovery. The measurement, he argued, was tangled up with the background light's own natural pattern, which could fake the appearance of a flow where none existed. Then came the heaviest blow. A powerful space telescope built to map the cosmic background with far greater precision turned its eye on the same clusters. Its team looked for the dark flow. They did not find it. If any such flow existed, they concluded, it had to be several times slower than Kashlinsky's claim, slow enough to fit comfortably within the ordinary rules of the cosmos. For many scientists, that settled it. The stakes made the fight bitter. A confirmed dark flow would rank among the most important discoveries in the history of cosmology, a signal from beyond the visible universe. A false alarm would be an embarrassment. With so much riding on the faintest signal, every side picked apart every step and no one wanted to be wrong. The dark flow, they decided, was most likely a ghost, a pattern the human mind and hungry instruments had conjured out of noise. Kashlinsky did not back down. He and his allies argued that the newer analysis had scrubbed away the real signal along with the noise, throwing out the baby with the bathwater. The debate hardened into a standoff that has never fully resolved. Some researchers still chase the dark flow, most treat it with deep suspicion. Here is why the story matters, even unresolved. It shows how thin the ice gets at the frontier of cosmology. When you measure the biggest motions in the universe, you are working at the ragged edge of what is possible, where a single subtle mistake can invent a monster, and where a real monster can hide inside the noise. Picture two expert trackers standing over the same faint print in the dirt. One swears it is the paw of a great beast headed over the ridge. The other kneels down, studies it, and says it is only the wind shifting the sand. Both are careful, both are skilled, and the print is too faint to prove either one right. That is the honest state of the dark flow, a footprint that may lead to something vast beyond the horizon, or maybe a trick of the sand. Nobody can yet say for certain. But the dark flow is not the only claim that our region moves in ways it should not. There is another anomaly, newer and harder to dismiss. built from the most careful map of galaxy motions ever made. And this one does not vanish when better instruments look. It says that our whole corner of the universe is flowing far too fast, across a stretch so wide that no known giant should be able to move it. And unlike the dark flow, this measurement keeps getting stronger. In 2023, a team led by the astronomer Richard Watkins built one of the most detailed maps of cosmic motion ever assembled. They used a catalogue holding careful distances and speeds for tens of thousands of galaxies, reaching far out into the universe. With it, they measured something called the bulk flow, which is simply the average motion of everything inside a huge sphere of space centered on us. It answers a clean question. Take a giant region around our galaxy. Which way and how fast is the whole thing drifting? For small spheres, the answer behaves. Nearby galaxies drift together at a modest pace, just as the standard model of the universe predicts. So far the rules hold. That agreement at small scales matters more than it sounds. It shows the method works, and the model is sound where we can check it up close. The trouble only appears when you widen the view, which is exactly where a deep hidden problem would choose to hide. Then they made the sphere bigger, and the flow refused to slow down the way it should. Here is the rule the flow was breaking. In the standard picture of the cosmos, the bigger the region you measure, the calmer its average motion should be. Zoom out far enough and all the local tugs cancel, leaving only a gentle drift. The larger the sphere, the slower the flow. That is the promise of a smooth universe. The Watkins team found the opposite of calm. Out at a distance of hundreds of millions of light years, the average flow was racing at hundreds of kilometers a second, roughly 4 times faster than the standard model says it should be at that scale. And the mismatch was not a small wobble. It sat at a level of confidence that scientists rarely dismiss, the kind of gap that usually means something is genuinely wrong. A second team, using a more cautious method, checked the same idea and found the same troubling result out as far as they could reach. The fast flow was not one group's error. It kept appearing. Sit with what this means. It is one thing for our galaxy to fall toward a giant. It is another for an entire region hundreds of millions of light years wide to be sailing along together, far faster than all the known mass in that region could ever explain. Picture a calm sea. Toss in a pebble, and you get local ripples, some water rushing this way, some that way. But zoom out to the whole ocean, and the average should be still. Now imagine you measure the whole ocean, and find it all sliding in one direction at once, as if the entire sea were being tilted by a hand too large to see. That is what the bulk flow looks like. A whole ocean, moving as one, faster than the tides can account for. If the measurement holds, and every fresh look so far has only strengthened it, then something is missing from our understanding. Either there is far more mass out there than we have found, pulling on a scale we cannot yet map, or the rules themselves, the equations that describe how the universe grows and moves, are incomplete. Both possibilities shake the foundations, and they point toward a suspicion that has been building among cosmologists for years. A suspicion about the very patch of space we call home. We may be sitting inside a hole. The suspicion goes by a few names. The local hole, the great local void, and it is far larger than the modest emptiness at our doorstep we met earlier. Here is the idea. When astronomers count galaxies in every direction out to about 1 billion light-years, they find fewer than they expect. Our whole region seems underpopulated, thinner in galaxies than the cosmic average. It is as if our galaxy sits near the middle of an enormous shallow bubble of below-average density, a hole in the cosmos hundreds of millions of light-years across. This is a different beast from the small local void we crossed before. That one is a nearby pocket we're being pushed out of. This one, if it is real, is a vast region we may be living deep inside, a hole so large it would dwarf every void and every giant in this story. And a hole that big would explain a great deal. Remember the too fast flow from a moment ago. If our region is underdense, then the fuller universe surrounding it would pull everything inside outward, toward the denser walls. Galaxies across the whole hole would stream toward its edges, all moving together, faster than a smooth universe allows. The great emptiness would act like a bowl, and every galaxy in it would roll toward the rim. That is exactly the kind of large, coherent motion the bulk flow measurements keep finding. Picture a wide, shallow valley carved into a plane. Rain that falls anywhere in the valley drains outward and down, toward the higher ground that rims it, all the water moving in a broad, unhurried sheet. If we live inside a cosmic valley of thin matter, then we and all our neighbours are that draining water, sliding toward the denser highlands around us. It is a strange thought. For most of this story, we have been falling toward giants. This idea flips the view. Part of our motion might come from fleeing an emptiness we are buried inside, drawn toward the richer universe beyond our lonely bubble. The local hole is still argued over. Some astronomers see clear signs of it in their galaxy counts. Others suspect the counts are fooled by the dust and blind spots that plague every survey, including that stubborn fifth of the sky we can never see cleanly. The jury is out. The idea is old, and it keeps returning. Astronomers first raised the possibility decades ago, noticing our neighbourhood seemed short on galaxies compared with deeper reaches of the sky. New accounts taken in infrared light that pierces some of the dust have kept the suspicion alive. If it holds, our whole cosmic address sits inside a rare, oversized bubble of below-average density, hundreds of millions of light-years across. But if the local hole is real, its consequences reach far beyond our own motion. It could tangle with one of the deepest puzzles in all of modern science, a crisis so serious that some researchers think it points to brand new physics. It touches the question of how fast the entire universe is expanding, and why two careful ways of measuring that expansion stubbornly disagree. Our humble corner of space, and the strange way it moves, might hold a clue to a mystery that spans the whole cosmos. The great crisis is called the Hubble tension, and it is keeping some of the finest minds in science awake at night. The universe is expanding. Everyone agrees on that. The disagreement is about how fast, and there are two main ways to measure it. One way looks at the early universe, reading the pattern in that ancient background light from just after the birth of everything, and using the known rules of physics to predict how fast the cosmos should be growing today. This method gives one clear number. The other way looks at the nearby universe directly. It measures the distances and speeds of galaxies close to us and simply watches how fast they're flying apart right now. This method gives a different number. The two numbers should match. They do not. The nearby universe seems to be expanding faster than the early universe predicts it should. The gap is small in raw terms, but it has refused to close for years, no matter how carefully anyone measures. It has grown into one of the sharpest cracks in modern cosmology. Now here is where our lonely corner of space comes in. If we really do live inside a large underdense hole, it could fake part of that gap. Inside a thin region, galaxies get pulled outward toward the denser surroundings, adding extra speed to their flight. A nearby astronomer measuring how fast local galaxies recede would clock them as moving a touch too fast, and would wrongly conclude that the whole universe is expanding faster than it truly is. In other words, some of the Hubble tension might be a local illusion, a trick played by the emptiness we happen to sit in. Picture standing in the middle of a crowd that is slowly spreading out to fill a plaza. If you happen to be standing in a thin spot, a gap where few people stand, the people around you rush away faster than average as the crowd equalizes. From your position, it would look like everyone was fleeing at high speed. You might guess the whole plaza was emptying faster than it really is, fooled entirely by the gap you stood in. That is the tantalizing possibility. Our motion, our too-fast flow, and our maybe hole could all be threads of the same knot, tied to the biggest unsolved puzzle about the fate of the universe. Not everyone buys it. Many cosmologists doubt that a local hole could be large enough or deep enough to explain the whole tension, and the debate is fierce and ongoing. The crack in the universe remains open. Still, the lesson is humbling. The strange rush of our galaxy through space, which began as a warm smudge on an old map, has led us step by step to the frontier of physics itself, to questions about what the universe is made of and how it will end. And it leaves us with a strange realization. Our hole, our giants, our voids are all local features. To know whether we are truly unusual, we have to see the pattern of the whole universe at once, the grand scaffolding on which every galaxy hangs. When astronomers finally mapped that scaffolding, they found a structure so vast and so beautiful that it changes how you picture reality itself. The entire cosmos, it turns out, is built like a web. Zoom out far enough, past our galaxy, past Laniakea, past the giants, and the universe finally shows its true shape. It looks like a web. Matter does not spread evenly across space. Over billions of years, gravity has gathered it into a vast, tangled structure. Long threads of galaxies stretch across the dark, and we call them filaments. Where the filaments cross, galaxies pile into dense knots, the great clusters and superclusters, and between the threads yawn enormous empty spaces, the voids. Astronomers call this pattern the cosmic web. It is the largest structure there is, the scaffolding on which every galaxy in existence hangs. Picture the froth of soap bubbles piled in a sink. The walls and edges of the bubbles are crowded with film. The insides of the bubbles are empty. Now stretch that froth across billions of light years and swap the soap film for chains of galaxies. That is the shape of the universe. Galaxies are strung along the threads like dewdrops caught on a spider's web at dawn. Our Milky Way sits on one such strand, part of a filament that feeds into the greater basin of Laniakea. Here is what the web reveals about our motion. Galaxies do not wander at random. They slide along the threads, drawn toward the dense knots where filaments meet. The whole flow we have been chasing, the fall toward the great attractor and Shapley, is really our galaxy sliding along its strand of the web toward a distant node. The voids matter just as much. Those empty bubbles are the source of the pushes we felt earlier. As matter drains out of a void and onto the surrounding walls, everything left inside gets driven toward the edges. The dipole repeller, the local void, the possible hole we may sit within, all of them are cells in the same great cosmic sponge. So the web ties the whole story together. The pulls come from the knots, the pushes come from the voids, and our galaxy rides the threads between them carried by the shape of everything. This structure grew slowly. In the young universe, matter was spread almost perfectly smooth, marked by only the faintest ripples, the very ripples we read in that ancient background light. Gravity seized on those ripples. Denser spots pulled in more matter and grew denser still. Emptier spots surrendered their matter and grew emptier still. Over billions of years, the faint ripples sharpened into the mighty web we see today. We are living inside the frozen record of the early universe, blown up to cosmic size. The pattern of galaxies around us is the fossil of those first tiny ripples, grown monstrous with time. Picture cream poured into coffee. At first it swirls in gentle streaks. Leave it, and the streaks stretch and branch into a delicate, tangled lace. The cosmic web formed the same way, matter drawn into ever finer threads by the slow, patient pull of gravity. And the web keeps going. Beyond Laniakea, beyond Shapley and Vela, the filaments stretch on, linking structure to structure across distances that stagger the mind. Follow those threads far enough, and you reach the largest things ever found. Structures so enormous they strain the very rules of how the universe is allowed to be built. Some structures in the cosmic web are so large they barely seem possible. In 2003, astronomers mapping millions of galaxies found one of them. A colossal sheet of galaxies, a wall standing in the web stretching across the sky. They named it the Sloan Great Wall, after the survey that revealed it. It runs for something like 1.5 billion light years, and it sits about 1 billion light years away from us. It is one of the largest structures ever mapped in detail, a rampart of galaxies almost too big to picture. Try to hold that size in your mind. Our whole supercluster, Laniakea, spans 500 million light years, and that already defeats imagination. The Sloan Great Wall is roughly 3 times longer still. If Laniakea is a continent, this wall is a feature that wraps a large part of a world. Then there is a claimed structure that dwarfs even that. By tracking the flashes of dying stars called gamma-ray bursts, some astronomers believe they traced a structure more immense still, a sprawling grouping of these bursts spanning as much as 10 billion light years. If it is real, it would be the largest thing ever found, so vast that light would need a large fraction of the age of the universe just to cross it. That size raises eyebrows for a reason. There may be a limit to how big a single structure the universe can grow in the time it has had. A wall 10 billion light years across pushes hard against that limit, and some scientists suspect it may be a pattern our eyes, and math conjured out of scattered points rather than one true object. The debate is live and unresolved. Here is the natural question. If these walls are so huge, are they pulling on us too? Are they part of the force dragging the Milky Way through space? The honest answer is that their reach is likely faint. Gravity weakens with distance, and these giants lie far beyond Shapley and Vela, 1 billion light-years and more away. At such range, even a monstrous wall tugs only gently on our small galaxy. The pulls that dominate our motion come from closer giants. Still, their existence carries a heavy message. The universe builds structures on scales that beg a belief, larger than our theories once expected, larger perhaps than the rules should allow. Picture zooming out on a map of a coastline. First you see your beach, then your bay, then the whole shore of your country, then a coastline wrapping an entire ocean. Each time you think you have reached the larger scale, a bigger pattern appears. The cosmic web plays that trick again and again, and the Great Walls are the biggest patterns we have yet dared to draw. And every one of these giants, each wall and void and supercluster, sits inside a single sweeping assumption that all of modern cosmology rests upon. It is the quiet belief that no matter where you stand or which way you look, the universe should appear the same. The giant walls, the strange flows, and the mysterious pulls have all begun to poke holes in that belief, and if it cracks, the damage reaches far beyond our galaxy's journey. It reaches the foundations of how we understand everything. Nearly all of modern cosmology stands on one simple idea. On the largest scales, the universe looks the same everywhere, and the same in every direction. Scientists call it the cosmological principle. It says that no place in the cosmos is special, and no direction is favoured. Zoom out far enough, and one giant chunk of the universe should look just like any other. Smooth, even, balanced. This idea carries enormous weight. It is the bedrock beneath our entire picture of the cosmos. Our theories of how the universe began, how it grew, and how it will end all lean on it. If the universe is the same everywhere, then the physics we measure here, in our tiny corner, holds true everywhere, and we can trust our maps of the whole. For a long time, the principle held up beautifully. The ancient background light is astonishingly smooth in every direction. Surveys of galaxies zoomed out far enough look reassuringly even. The universe seemed to obey the rule. Then the cracks appeared, and they are exactly the cracks in this story. The dark flow, if it is real, points one favoured way, which the principle forbids. The too fast bulk flow shows our whole region streaming together far beyond what a smooth universe allows. The pile-up of giants near us, Shapley and Vela side by side, hints that our patch may be lumpier than average, and the possible hole around us suggests we might sit in a special place after all, near the centre of a great emptiness. Each of these, on its own, might be a fluke or a measurement error. Together they form a nagging pattern. They whisper that the universe might be less smooth, less even, and less fair than we have always assumed. If the cosmological principle is wrong even a little, the damage runs deep. Many numbers we trust, including how fast the universe expands and how old it is, are calculated on the assumption that our view is typical. Learn that our view is skewed, and those numbers begin to wobble. Picture a scientist studying the whole ocean by measuring one small cove, confident that the entire sea behaves like their cove. Their conclusions are only as good as that assumption. If their cove happens to be strange, unusually calm or unusually deep, then everything they concluded about the ocean is quietly wrong. Cosmologists face the same worry. We can measure only our own cove of the universe, and we have been assuming it is ordinary. Most cosmologists still defend the principle. They argue that the anomalies are small, that better data will smooth them away, that our cove is typical after all. They may well be right. The principle has survived many challenges before. History gives them reason for that confidence. Time and again, an anomaly that looked like a crack in the cosmos turned out to be a flaw in the data or a trick of the instruments. When the entire model of the universe is on the line, deep caution is the wise first response. But the doubt is real, and it is growing, and it forces a sharp question about the strange flows we have measured. If our galaxy really is moving faster than the known mass can explain, then one of two deep things must be true. Either the universe hides far more matter than we have ever found, or the law of gravity itself, the rule that has guided every step of this story, breaks down on the larger scales. Both answers would rewrite the textbooks. Scientists have wrestled with a puzzle like this before, and it led to one of the biggest ideas in all of science. Decades ago, astronomers noticed that galaxies spin too fast. The stars at their edges whirl so quickly that each galaxy should fly apart unless some unseen mass is holding it together with extra gravity. That hidden mass earned a name, dark matter. It appears to outweigh all the ordinary matter, all the stars and gas and planets, by a wide margin. We cannot see it. We feel only its pull. So when our whole region streams too fast for the visible giants to explain, the first suspect is the same, more hidden mass. Perhaps great clumps of dark matter and undiscovered clusters still lurk out of sight, especially behind that stubborn fifth of the sky we can never see cleanly. Vela hid there for a century, others may hide there yet. Add enough unseen mass, and the too fast flow might make perfect sense. That is the comfortable answer. It keeps our laws of physics intact and simply asks us to keep searching for what we missed. There is a second answer, and it is far bolder. Perhaps our law of gravity itself is what fails us. Perhaps the equations we trust across the cosmos run subtly wrong on the larger scales, and there is far less hidden mass out there than we believe. The rules we use to describe gravity were built and tested on smaller stages in the solar system and its neighbourhood. A handful of scientists suspect that across the vast reach of superclusters and flows, gravity behaves a little differently than our equations claim. Adjust the law of gravity in the right way, and you might explain the strange motions with little or no hidden mass at all. This idea is a minority view, and it faces steep obstacles. Our current law of gravity has passed test after test with breathtaking precision, and changing it is a drastic step that most scientists resist. But the anomalies keep returning, and as long as they do, the bold idea refuses to die. The truth may lie between the two, or somewhere no one has yet guessed. That is the honest state of the frontier. We have a fast flow we cannot fully explain, and two grand suspects, hidden mass and broken gravity, each of which would reshape our understanding of everything. Picture a detective standing before a locked room where a fortune has gone missing. One theory says the gold is still inside, sealed in a wall no one has opened. The other says the gold was never where we thought, and our very idea of where it should be is mistaken. Both would crack the case wide open. Both change the whole story, and the detective cannot yet tell which is true. For now, the puzzle stands. The Milky Way races through space faster than we can fully account for, tugged and shoved by giants and voids, and the deepest reason why remains just out of reach. Yet the answer is coming. It will arrive not from guesswork, but from a new generation of machines switching on right now, instruments so powerful they will map the flow of the cosmos in detail no one has ever held, and pierce the last dark corners of the sky. The tools that will solve this mystery are already opening their eyes. For all its terror and grandeur, this mystery may not stay a mystery much longer. A new age of astronomy is beginning, built on machines far more powerful than anything the Seven Samurai ever had. These instruments are designed to map the motion and structure of the universe on scales we could once only dream of, and they are switching on now, in our own lifetimes. One is a great survey telescope high in the mountains of Chile, built to photograph the entire southern sky again and again, night after night for years. It will catalogue billions of galaxies and track their positions and motions with staggering precision. Where the old maps held tens of thousands of galaxies, this one will hold billions. It will draw the flow of the cosmos in a detail that makes today's charts look like rough sketches. Another is a vast array of radio dishes, the heirs to the telescopes that first pierced the zone of avoidance. Radio waves sail straight through the dust of our galaxy, so these dishes can finally map the hidden fifth of the sky where giants like the Great Attractor and Vela have lurked. The blind spot that has haunted this whole story may at last be filled in. Still others are surveys built to measure the distances to millions of galaxies at once, stitching together a three-dimensional map of the universe deep enough to test the strange flows head-on. They will show, in hard numbers, whether our region truly moves too fast, whether we sit inside a great hole, and whether the pattern of the cosmos really favours one direction. Within a single generation, these machines could settle questions that have stood for decades. Is the dark flow real, or a ghost in the noise? Is the bulk flow truly too fast for the rules? Is there hidden mass out there, or is gravity itself in need of repair? Do we live in an ordinary patch of the universe or a strange one? We happen to live at the exact moment when the tools are finally catching up to the questions. Generations of astronomers felt these mysteries and lacked the eyes to solve them. We may be the ones who finally see clearly. Picture the gap between a sailor of old charting a coastline by eye from the deck of a wooden ship and a modern mapmaker with satellites circling the whole planet. The sailor felt the currents and guessed at what lay beyond the horizon. The mapmaker simply looks and knows. Astronomy is crossing that same divide, from guessing at the great flows to measuring them outright. The force pulling the Milky Way through space has guarded its deepest secrets for as long as humans have looked up. Those secrets are now within reach. But even as we sharpen our vision and close in on the answers, one question sits beneath all the others, patient and unavoidable. We have traced where we are going. We have named the giants ahead. We have measured our breakneck speed. So where does it all end? After billions of years of falling, what is the final fate of our galaxy, our flow, and the whole vast machinery of the cosmos we ride? The universe has an answer waiting, and it begins with a finish line we can never reach. We have been falling toward the great attractor for billions of years. It feels like we must arrive eventually. We will not. The reason is the expansion of the universe, and it plays a cruel trick. Space itself is growing. Every second, the distance between far-apart galaxies stretches wider, as if the whole cosmos were a rubber sheet being pulled in all directions at once. Our galaxy falls toward the giants ahead, yes, but the space between us and those giants is stretching at the same time, pushing them away. For nearby things, our falling winds, there is a boundary hidden in all this, a line cosmologists can roughly draw. Inside it, gravity keeps its grip and objects stay bound to us for good. Outside it, expansion wins forever, and whatever lies there is lost to the growing dark no matter how hard it falls our way. The great attractor sits on the far side of that line, out in the territory that slips beyond reach. Our little local group is bound tightly by gravity, close enough that the stretching cannot tear it apart. Those galaxies will stay with us. We will fall together and one day merge together. For the distant giants, the stretching wins. The great attractor lies far enough away that the growth of space between us outruns our fall toward it. Every year we move a little closer through our own motion, and every year expansion carries it a little farther off. The second effect is stronger. The gap grows, so the finish line runs away from us faster than we can chase it. Picture a runner sprinting toward a doorway at the end of a hall. Now imagine the hallway itself is stretching, the far wall sliding backward faster than the runner can advance. The runner pours out everything, legs burning, and still the door drifts away. That is our galaxy chasing the great attractor. We run at over 1,000,000 miles an hour and the target retreats even faster. We will never touch it. We will never plunge into Shapley. We will never meet the monster at the end of the fall. There is a strange dignity in a fall that never lands. For billions of years our galaxy has poured itself toward the giants, and for billions more it will keep pouring, always closing the gap through its own motion, always losing it again to the swelling of space. The chase runs forever, and the capture stays impossible. We are held in a permanent, graceful plunge toward a floor that keeps sinking away. The whole terrifying pull that has shaped our journey, the force that first showed up as a warm patch on the sky, will draw us for eternity without ever landing us. That should feel like a relief, and in a way it is. No cosmic whirlpool is going to swallow us whole, but the same force that saves us from the giants carries a colder fate. The expansion of space is speeding up. It is being driven by something we barely understand, a mysterious energy woven into the fabric of the cosmos, pushing everything apart harder and harder as time goes on. That accelerating push does more than keep the great attractor out of reach. Given enough time, it will tear the entire visible universe away from us, one galaxy at a time, until the sky itself goes dark. To understand the true fate of our fall, We have to meet the force that will one day steal the whole cosmos from view. The force driving the runaway expansion has a name that admits how little we know about it. Dark energy. It fills all of space. It has no glow, no shape, no source we can point to. We know it exists only by what it does, which is to push the universe apart faster and faster over time. And there is a staggering amount of it. Dark energy makes up the great majority of everything in the cosmos, far outweighing all the stars, gas and galaxies combined. Here is the part that should send a chill down your spine. Because the expansion is speeding up. The distant galaxies are not just drifting away, they are accelerating away, and one by one, over the ages to come, they will cross a line. When the space between us and a far galaxy stretches fast enough, its light can no longer reach us at all. From that moment on, it vanishes from our sky forever, sealed off beyond a horizon we can never see past. This is already the fate written for almost everything we can observe. The giants of this story, Shapley, Vela, the Great Attractor, are all so distant that dark energy is winning the tug-of-war against their gravity. Over the coming eons they will fade, redden, and slip away, carried off by the swelling of space until they blink out of view. The cosmos is quietly emptying, not through violence, but through distance. Picture a vast fireworks show at night, the sky full of bright bursts. Now imagine each spark is drifting away from you, and the faster ones fade to nothing as they go. Slowly the sky clears, spark by spark, until only the few closest embers remain, and beyond them, pure black. That is the future of our night sky, a slow subtraction until almost nothing is left. There is a strange mercy in the timescale. This is not tomorrow, or 1,000,000 years from now. It unfolds over tens and hundreds of billions of years, far longer than the current age of the universe. We have unimaginable stretches of time before the sky goes dark, but it is coming. And it hides a haunting thought about knowledge itself. If future astronomers, born long after the giants have faded, look up at their sky, they will see only the merged remains of our own local family of galaxies, floating alone in a black void. Everything else will have vanished. The expansion, the distant superclusters, the evidence of a universe once teeming with structure, all of it gone from view. They would have no way to know any of it ever existed. We happen to live at a rare moment, early enough to still see the giants that pull us and the light that reveals our motion. We are among the lucky few who get to read the true story of the cosmos before the pages are torn out. That gift makes the whole terrifying tale of our fall feel different, less like a threat, more like a privilege. Still, a nagging fear remains. All this talk of monsters and voids and forces that empty the sky, it is natural to wonder quietly whether any of it puts us in danger right now. It is time to answer that honestly. Let us be plain about the danger, because the truth is calmer than the fear. The Great Attractor will never reach us, and we will never reach it. The expansion of space guarantees that the distant giants stay distant. There is no cosmic drain about to swallow the Milky Way, no whirlpool waiting to crush us. The pull is real, and it is vast, and it is also, for us, completely survivable. We have been living inside it happily for the entire history of life on Earth. The speed is nothing to fear either. Our galaxy has been racing at over 1,000,000 miles an hour for billions of years, and you have never felt a bump. Motion through space, even enormous motion, is smooth. There is no wind out there, no friction, nothing to jostle the ride. The whole solar system sails along in perfect calm. Even the emptying of the sky, the slow theft by dark energy, lies almost unimaginably far in the future. Tens of billions of years will pass before the giants fade from view. Our own sun will end its life long before then, in about 5 billion years, swelling into a red giant and reshaping the solar system. Whatever becomes of humanity, the darkening of the distant sky is a worry for a universe unrecognizably older than ours. So the honest answer is this: the forces in this story are titanic, but they are gentle to us on every timescale that matters. We are not being crushed, we are being carried. It helps to hold the sheer sweep of time in mind. The pull that shapes our motion has been at work since long before the first living cell appeared on Earth, and it has harmed nothing in all those ages. A force can be titanic in scale and still be perfectly gentle to the tiny worlds riding inside it. Scale and danger are simply two different things. There is a real collision in our future though, and it is worth knowing about, because it is far closer than any giant. Our neighbour Andromeda, the great spiral galaxy nearby, has long been on a path toward us. For years, astronomers expected a certain head-on collision in roughly 4 billion years, a merger that would fling our two galaxies together and eventually braid them into one. Newer studies have softened that certainty, suggesting the meeting is less guaranteed than once thought, more a matter of chance across the deep future. But a close encounter, and quite possibly a merger, still lies ahead. Here is the reassuring part. A galaxy merger sounds like the ultimate catastrophe, two cities of stars smashing together. In truth, galaxies are mostly empty space. Stars are so far apart that when galaxies merge, almost none of them actually hit. The two star clouds glide through each other like two swarms of fireflies passing in a field, reshaping over hundreds of millions of years into a single new galaxy, with barely a star touched. Picture two vast flocks of birds crossing paths in a wide sky. From far away it looks like a violent clash. Up close, the birds simply weave between one another and fly on. That is what awaits the Milky Way and Andromeda, a grand reshaping, not a demolition. This is the future that gravity is quietly building for us, and it points to a deeper truth about our place in the cosmos, one that survives, even as the distant giants fade away. We're not alone out here, we travel with a family. Amid all the pulling and pushing and vanishing, one thing stays loyal to us: our own small group of galaxies. The Milky Way, Andromeda, and dozens of smaller galaxies are bound tightly together by gravity into the local group. This little family is close enough, and its grip is strong enough, that the expansion of space cannot pry it apart. While the distant giants drift away and the far sky slowly empties, our local group stays whole. It is the raft we ride through the cosmic ocean. That fact reshapes the whole ending of the story. Yes, dark energy will one day carry off the visible universe. Yes, Shapley and Vela and the Great Attractor will fade beyond reach. But our raft holds. The galaxies we can touch, the ones bound to us by gravity, remain our companions for the long haul. In the far future, gravity will finish knitting the local group together. Andromeda will merge with the Milky Way. The smaller galaxies will fold in over time, and the whole family will settle into a single vast galaxy, alone in its patch of space, sailing on long after the rest of the cosmos has slipped over the horizon. There is something quietly beautiful in that. The forces of this story do more than pull things apart. Up close, they also bind. They gather. They build islands of light that endure. Think of the whole picture we have assembled. Our galaxy falls toward the Great Attractor. The Great Attractor falls toward Shapley. A hidden Vela lurks behind the dust. A void shoves us from behind. A larger emptiness may cradle us. Dark energy drives the giants beyond reach, and through all of it, our little raft of galaxies holds together, carrying us forward as one. We're a single boat on an immense moving sea, pulled by currents that reach past the edge of sight, riding forces we're only beginning to understand. Picture a small wooden raft on a river at night. The current is powerful and strange, sweeping the raft toward distant shapes it will never reach. Above, the stars slowly drift and fade, and yet on the raft itself, the travellers sit close together, safe, warm, carried steadily onward. That is us. That is our galaxy and its family riding the great flow. For most of human history, we did not even know the river existed. We thought the stars were fixed, the heavens still, our world at rest. It took centuries of patient work and eyes that could see through dust and read the oldest light in the sky to reveal the truth. We are moving. We have always been moving. And the map of that motion is the map of our true home. So the pull that first frightened us turns out to be something else entirely. It is the thread that ties us to the largest structures in creation. It is the reason we can trace the shape of the local universe at all. The force dragging us across space is also the force that taught us where we live. Which leaves one last question. If we can never reach the giants, and the sky will one day empty, then what does all this motion truly mean for us, here, now, on one small planet riding the flow? Step back and look at how far a single warm smudge took us. It began with a faint crookedness in the oldest light in the universe, a patch of sky a hair warmer than the rest. From that whisper, astronomers deduced that our entire galaxy was moving. From the motion, they hunted down the Great Attractor. From the Great Attractor's weakness, they found Shapley. From the full flow, they drew Laniakea and gave our galaxy a true address. From the leftover speed, they uncovered the void that pushes us. From the dust, they pulled a hidden veiler. And from the largest motions of all, they stumbled onto cracks in physics itself. Every answer opened a bigger question. Every giant sat on a leash held by a larger one. Every map turned out to be one district of something vaster. That is the real gift of this story. Chasing the force that pulls us, forced humanity to map the local universe, to weigh the invisible, and to find the edges of what we understand. We went looking for a monster, and came back with a portrait of our whole cosmic neighbourhood. And the portrait is humbling. We are a single galaxy, on the ragged edge of one supercluster, inside a possible hole, riding a flow toward giants we will never reach, in a universe that will one day carry those giants out of sight. By any measure of size, we are almost nothing. And yet size makes a poor ruler for worth. A thing can be vanishingly small, and still be the one part of the cosmos that has come to understand the rest of it. That, as far as we know, is exactly what we are. Yet look what that almost nothing has done. From one small planet, orbiting one ordinary star on the outskirts of one galaxy among 100,000, we reached out with clever instruments and traced motions that span hundreds of millions of light years. We felt a pull we cannot see, named the giants behind it, and glimpsed forces that shape the fate of everything. Picture a single grain of sand on a vast beach, somehow able to map the whole coastline, sense the tides, and chart the pull of the distant sea. That is what our species has managed. A grain of sand that learned the shape of the ocean. The force pulling the Milky Way through space is terrifying in scale. It is heavier than 10,000 galaxies. It reaches across distances light needs hundreds of millions of years to cross. It bends the paths of entire superclusters, and we, riding our small raft of stars, are caught in its grip whether we like it or not. But we are also the ones who found it. We are the ones who can look up, understand that we are falling, and feel awe instead of only fear. In a universe destined to empty and darken, we live at the rare bright hour when the whole story is still visible, still readable, still ours to know. So the next time you feel the ground beneath you and think you're standing still, remember the truth. You are moving. Faster than any rocket in every direction at once, pulled by giants and pushed by voids, riding a river of galaxies through the dark. You're not standing still, you never were, and now at least you know which way you're going and what waits out there in the deep, quietly pulling you home.